So in the previous movie, I analyzed the data for the first trial. Here are all the calculations associated with the second trial. Here's our average moles of sodium carbonate when I use the 10 cubic centimeters in the mixed solution at first. That's the moles of the sodium hydroxide. Doubled the volume here, so I double the number of moles there. And so in order to match up the two, I just calculate the sodium hydroxide to the sodium carbonate ratio between the two, which of course should be the same. Now to answer the post-lab questions, this first page I'm not going to be asking you to submit for me. This is to show your teachers. But there's phenolphthalein and there is methyl orange. Methyl orange is a diazo compound, and you'll study that when you get into your year 13 if you haven't already started it. Parts of each molecule make it an acid-base indicator. Well, indicators are weak acids, so they've got to have either an acidic proton or the ability to accept an acidic proton. In phenolphthalein, it's that OH there. Of course, it could be that OH there, but one of those OH is on the so-called phenol group. And then with methyl orange, it's actually this diazo group. The nitrogen has a lone pair there which can attract an H+. So this is the base form of methyl orange. After it's in a sufficiently acidic solution, it accepts a proton H+, and that will change the color. This is the phenolphthalein acidic form, which then, when it becomes basic enough, it loses an H+ and changes from colorless to pink. 3 equivalence points, because there are 3 neutralizations: the sodium hydroxide, and then the sodium carbonate to hydrogen carbonate, and then the hydrogen carbonate to carbonic acid. Which neutralization is not shown by an indicator? Well, it's the first one, the sodium hydroxide, because the first indicator is phenolphthalein, and that changes color from pink to colorless when we've neutralized not just the sodium hydroxide, but the first batch of the sodium carbonate. So what indicators could I use for this one? Well, this happened at a very high pH. It was somewhere between 11 and 13. And there's not many indicators that change color between 11 and 13. Most of them have done their color changing well before that. But one that you could use is indigo carmine. If you pick one that's not indigo carmine, you can check with your teacher to see if that one would work. Mole ratio of sodium hydroxide to sodium carbonate in a mixed solution. Well, I calculated that from the full data sheet using the 10 cubic centimeter of the mixed solution, it was 0.776. Using the 20 cubic centimeter, it was 0.759, so the average about 0.767 ratio. And now finally, I made 250 cubic centimeters mixed solution. How many grams each of the sodium hydroxide and sodium carbonate did I use? Well, I'm going to use the data from when I used 20 cubic centimeters of the mixed solution, because the bigger the measurement you make, the smaller the percent error inherent in the glassware or any other sort of reproducible standard parts of the experiment. Now, the average for the 20 cubic centimeter data was in that 20 cubic centimeters. I had 1.88 times 10 to the minus 3 moles of sodium hydroxide, 2.488 times 10 to the minus 3 moles of sodium carbonate, turning moles to grams, multiplied by 40 for the sodium hydroxide, multiplied by 106 for the sodium carbonate. And this is, of course, the grams in 20 cubic centimeters. I'm interested in the grams in 250 cubic centimeters, so I just multiply by 250, divide by 20. And what I find is that I used a little bit less than 1 gram of sodium hydroxide and 3.3 grams of sodium carbonate. Hope you enjoyed this particular experiment. It's a funny old one to put in there, but it is one that I think illustrates some calculations and some concepts in a fairly clear fashion. At least I hope you found it was a fairly clear fashion.